What factors affect stability in feedback control systems? Imagine trying to keep a bicycle balanced while riding over uneven ground. Just like that, feedback control systems aim to keep a machine steady despite disturbances. But what makes some systems stay stable while others wobble out of control? Let's find out. The first thing to look at is where the poles of the system are located in the complex plane. If the poles are in the left half of the plane, the system is stable. That means it will return to normal after a bump. If any poles sit on the imaginary axis, the system is only marginally stable. It might stay steady for a while but can become unstable with small changes. Poles in the right half of the plane spell trouble, causing the system to grow unbounded and become unstable. Next, the feedback gain, which is how much the system reacts to errors, plays a big role. If you increase the gain too much, it can push the poles toward the imaginary axis or even into the right half plane. That can make the system oscillate or become unstable. Engineers use tools like the Routh-Hurwitz criterion to find the right gain range that keeps the system stable. The characteristic equation, which comes from the system's transfer function, helps analyze stability too. By applying the Routh-Hurwitz test, you check the signs of the coefficients. If there are any sign changes, it means the system has poles in the right half plane and is unstable. This is a quick way to see if your control system will hold steady. Frequency response measures like phase margin and gain margin tell us how close the system is to losing stability. A larger phase margin means the system can handle more phase lag before becoming unstable. Similarly, a bigger gain margin means the system can tolerate more increase in gain without going unstable. These margins help engineers design more robust systems. The Nyquist stability criterion is another handy tool. It involves plotting the open-loop response and counting how many times it encircles the critical point in the complex plane. If the plot encircles the point in a certain way, it indicates the system's stability or instability. It's like a visual check that confirms whether your feedback loop is safe. The root locus method shows how the poles move as you change the feedback gain. By watching the paths of the poles, you can see at what gain levels the system stays stable or becomes unstable. It's a visual way to tune your system for the best stability. Finally, real-world factors like delays, nonlinearities, and higher-order dynamics can impact stability. For example, if there are delays in the feedback signal, they can cause phase lag and push the system toward instability. External disturbances and noise can also make the system wobble or drift away from equilibrium. In electrical engineering, these factors are vital when designing amplifiers, power supplies, or oscillators. Engineers carefully analyze pole locations, gain settings, and frequency response to keep systems stable. They use tools like Routh-Hurwitz, Nyquist plots, and root locus diagrams to make sure everything runs smoothly. So, in short, the stability of a feedback control system depends on where the poles are, how much feedback gain you use, the system's parameters, and how it responds across different frequencies. By understanding these factors, engineers can build systems that stay steady, even when faced with surprises.